day to my dear judges. I am Mohnish Sundar, studying in ninth grade in Shishugriya High School, and today I am going to demonstrate an experiment about Newton's law of cooling as part of my RYSI second stage submission. The aim of this experiment is to study and compare the rate of cooling of different liquids using Newton's law of cooling and to determine how the specific heat capacity of each liquid affects its cooling rate. The uniqueness of my experiment is that it compares how different liquids cool using Newton's law of cooling instead of studying just one liquid. All liquids are tested under the same condition, making the differences in cooling rates easy to observe. It also connects these rates to each liquid's specific heat capacity. The materials are simple and easily available, making the experiment easy to perform. Overall, its simplicity and clear results make it practical and meaningful. The materials required for this experiment are 1 beaker of oil, 1 beaker of milk, 1 beaker of water, a Bunsen burner, 2 temperature probes, and another Bunsen burner. The hypothesis for this experiment is that 1. The rate of cooling of a liquid is directly proportional to the temperature difference between the liquid and the surrounding air. 2. All liquids will follow Newton's law of cooling, showing an exponential decrease in temperature with time. 3. Each liquid will have a different cooling constant, K, depending on its physical properties such as viscosity and surface behavior. 4. The liquid with the highest K value will cool the fastest, while the one with the lowest K value will cool the slowest. Therefore, it is expected that water will cool fastest, followed by milk, and gingerly oil will cool the slowest. The procedure and experimental setup for this experiment is to keep all liquids, each of 100 ml, ready in 3 different glass beakers on a table. Then heat water, milk and oil to 80 degrees Celsius using the Bunsen burner. Place the thermometer probes in each container at a time. Keep the room free from wind or sunlight to maintain stable surroundings. Immediately start the stopwatch and record the temperature of each liquid for every 1 minute. Keep repeating for at least 30 minutes or until all the liquids reach room temperature. Observation and calculation. The temperature of the surrounding when the reading was taken was 26.9 degrees Celsius. I have recorded the values of the temperature of water, milk and oil starting from 80 degrees Celsius till the time it reaches the room temperature and calculated the difference between the temperature of the liquid at the time T minus the room temperature and entered it in a separate column. Thus, from the table, we can deduce that the rate of cooling of an object is directly proportional to the temperature difference between the object and its surroundings, and the rate of change of temperature can be calculated using the formula the minus of the cooling constant multiplied with the temperature of liquid at time T minus the room temperature. I have calculated the average cooling rate for water, milk and gingerly oil and entered the values in the table here. I have also plotted a time versus rate of cooling graph for water, milk and oil using the recorded values, and from the graph it is observed that the rate of cooling decreases or becomes less negative with time for all 3 liquids, water, milk and oil, showing that the cooling process slows down as temperature approaches room temperature. Among the 3 liquids, oil cools the slowest, having the least negative rate of cooling values. Water cools the fastest, having the most negative rate of cooling values, and milk lies in between. Conclusion. This experiment shows that the rate of cooling depends on the specific heat capacity and thermal conductivity of the substance. Milk, having higher water content and better heat transfer, loses heat faster, while oil, with lower thermal conductivity, retains heat longer. Thus, the experiment confirms Newton's law of cooling, where the rate of cooling is proportional to the temperature difference between the liquid and its surrounding. So next time your coffee gets cold, remember, it's not magic, it's Newton's law of cooling. And that's how Newton explains how your coffee goes from steaming hot to just right.